Hi everyone. Today we're going to be beginning our notes on 2.2 piecewise functions. I want to start with this first one. We're going to look at the function here. This is a piecewise function, and we're going to graph it, determine whether it's a function, and then evaluate the function for each of these x values. So to begin, to graph this piecewise function, I'm going to start by creating a table of values, x, f of x. And I noticed that the key values in this piecewise function are, there's only one, x equals 1. So I'm going to choose a few points centered around x equals 1. I'm going to choose points like maybe -1, 0, our key value 1, and then maybe another after that too. To evaluate the function at x equals -1, I'm going to first determine which of these inequalities that satisfies. Well, -1 satisfies this inequality, the bottom one. So x is less than 1. That is true for -1. So plugging in -1 into this part of the equation, x squared plus 3, and evaluating, we get the quantity -1 squared, which is +1, plus 3 is 4. Evaluating the function at 0, so again, we have to determine which inequality this satisfies. Again, it's this one right here. So when we plug in 0, so we have 0 squared plus 3 is 3. And then let's go ahead and evaluate 1. That's our key value. So this is true for the top inequality. So let's go ahead and plug in 1 into this top expression. 2 times 1 plus 1 is 2 times 1 is 2, plus 1 is 3. And then finally, for x equals 2, we have this top expression here. So we'll plug in 2. 2 times 2 is 4, plus 1 is 5. Let's go ahead and plot these points. So the first point, -1, 4, is right here. 0, 3 is our y-intercept. 1, 3 is right here. And we have 2, 5. So 2, 5 is right here. Now, all of these points exist on the function, but there's something that's going on at x equals 1. And notice that we evaluated for this top expression here. But we do need to know, because this function is all values up to 1 but not including, we also need to know what the function is approaching. So if we evaluate this expression, x equals 1, for x equals 1, then we can determine where the left-hand side of our function should look like. So when we plug in 1 here, we have 1 squared is 1 plus 3 is 4. So I know that this function on the left-hand side is a quadratic, x squared plus 3, is appearing to be going up to the point 1, 4, but not including. So we're going to put an open circle there. Okay. So now we can sketch in the graph here. So remember, the left-hand portion is like a quadratic. Let me redraw that real quick. And the right-hand side is a linear function, 2x plus 1. So that just continues in a straight line. Don't forget your arrowheads. This does extend infinitely in both directions. So is this a function? Does this pass the vertical line test? Is there any place on this graph that crosses the graph twice? And the answer is no. So this is a function, yes. Evaluating for f of -2, we are going to plug it into the second expression here. So plugging in -2, we have the quantity -2 squared is +4 plus 3 is 7. Evaluating for 6, we plug in the top expression. So 2 times 6 plus 1 is 13. And then evaluating f of 1, again, this is that key value. This goes into the top expression. So the function is evaluated to 3. All right, let's try another. Number 2, now we have 3 pieces here. We have something going on all the way up to 0, between 0 and 5, and then after 5. So let's go ahead and construct a table of values and choose some of those points. So I want to choose, let's go ahead and write our table of values. I want to choose a value that is less than 0, so we'll say -1. I want to choose that key value 0, maybe a point in between, so we'll do 2. I want to choose that other key value 5, and then maybe another point after that key value 6. All right, so let's go ahead and evaluate. So for x equals -1, we're going to plug it into this top expression. The quantity -1 squared minus 1 is equal to 0. Plugging in 0, again, this is going to go into our top expression here. 0 squared minus 1 is -1. Plugging in 2, this goes into our middle expression. So 2 fits this domain here. So we're going to plug in 2 here. We have 2 times 2 minus 1 is positive 3. We plug in 5. So again, that fits that middle expression as well. So 2 times 5 minus 1 is 9. And then finally, plugging in 6. This goes in the last expression. Well, there's nowhere to plug in for x. The value is just 3. Okay. So let's go ahead and start graphing this. The left-hand piece is a quadratic with a y-intercept of -1, and it opens upward. So this goes all the way up until x is equal to 0 and everything to the left of that. So we have the point -1, 0. We have 0, -1. We have the point -2, 3. Maybe you could even do -3, 8. But just enough points, maybe just 2 points on there is plenty to graph this quadratic piece. After that, we have the linear piece, 2x minus 1. So this has a y-intercept of -1 and a slope of 2. So here we have a y-intercept of 1. Well, that point already exists from that first piece. After that, we have the slope of 2. So we're going to go up 2 and to the right 1. And we're going to do that all the way up to x equals 5. So I'm going to do that all the way up here. We'll connect our dots and we have the linear piece. Or one of the linear pieces, I should say. And the last piece is just the horizontal line, y equals 3, but only for the domain x is greater than 5. So y equals 3 is this line here, and it goes all the way to the right. Just a horizontal line. Okay? The function for this third piece does not exist at x equals 5. It's only x greater than 5. So we do have to put a hole there at 5, 3. Okay, let's go ahead and evaluate. Well, this is a function. So does this pass the vertical line test? It sure does. So this is a function. Evaluating f of -3. So plugging in -3, that's that first piece. We have the quantity -3 squared minus 1 is 8. Our y-intercept, f of 0, we evaluated for already. That's that first piece again. So we have 0 squared minus 1 is -1. And then finally, evaluating f of 5, that's our other key value. That's that middle expression there. 2 times 5 minus 1 is 9. And we can also obtain that from the graph. Let's try another. All right, so for number 3, here we have 2 pieces, both quadratic pieces. So this, our key value here is at 0. So I'm going to go ahead and construct a table of values. And I'm going to choose 1 point to the left of 0, 1 point to the right of 0, and then also 0. So let's do -2, -1, 0, 1, and 2. We'll get plenty of points there. So plugging in -2, this goes in the top expression. So the quantity -2 squared is positive 4. -1 is again also the top expression. So the quantity -1 squared is positive 1. 0 again goes in the top expression. So 0 squared is 0. Y-intercept is also the origin. Plug in 1, this goes into the bottom expression because 1 is greater than 0. So we have 1 squared is 1, make it negative, and then add 4 is positive 3. 2, so we plug in 2, we get 2 squared is 4, make it negative, and add 4 is 0. Okay, so let's go ahead and plot some of these points. So -2, 4 is right here, -1, 1, the origin 0, 0, 1, 3, and 2, 0. So remember, the left-hand piece is the parent function for a quadratic x squared. So it's centered at 0, 0, 0, and it opens upward. So I'll sketch in that graph. And then the other one is another quadratic with a y-intercept of 4, and it opens downward. So because our y-intercept is 4, but it does not exist in this part of the function, it must be a hole. And then again, it opens downward. And we can see that here. So is this piecewise function a function? Yes, it is. It passes the vertical line test. F of -4, let's go ahead and evaluate. So that's going to be in the top expression. The quantity -4 squared is positive 16. F of 0, again, goes in the top expression. So 0 squared is 0. And f of 3 in the bottom expression, we get 3 squared is 9, make it negative, is negative 9, and add 4 is negative 5. Okay. Now let's go ahead and write the piecewise functions from the graph. So here we have a couple of graphs. Let's start with number 4. I see two pieces to this, so I'm going to go ahead and start defining my piecewise function. F of x is equal to the piecewise function. We'll start on the left-hand side. I notice that this is a linear piece, and it has a slope of 1. We're going up 1 into the right 1 every time, and it has a y-intercept of 0. So this is a function y equals x, and the domain for this piece is, we can say, x less than 0. Yes, you could say x is less than or equal to 0, and we'll see that in just a moment. For the second piece, we have another linear piece, but this time the slope is positive 2. We go up 2 into the right 1. So, and our y-intercept is 0. So this piece has the equation y equals 2x. For the domain, x is greater than or equal to 0. We're looking at all the values to the right of 0 and including. So could you have called this part less than or equal to 0? Yes, as long as this part is then strictly greater than. You cannot have both greater than, or you cannot have both not equal to, or both equal to, right? You need one equal to and the other not. Okay, so for number 5, we'll call this one f of x as well. A different function, different graph. I see that the left-hand piece over here is a linear function, and it has a slope of positive 1. So this is y equals x, but then we have to determine the y-intercept as well. If we were to extend this line, we would see that it would cross the y-intercept right here at 0, 5. Therefore, the y-intercept is 5. So we have the expression x plus 5. The domain of this is going to be everything less than or to the left of negative 2. So we have x is less than negative 2. For the second piece, we have the horizontal line at y equals negative 1. And the domain for this is everything greater than or equal to negative 2. Now in this case, it does have to be this way, where this is less than and this is greater than or equal to, because we have an open circle up here and a closed circle here. Okay, let's try a few more. Flip the page, number 6. Here we have 3 pieces, each linear. So we'll call this f of x is equal to the piecewise function. This left-hand piece, we have, it doesn't quite cross, but this has a slope of 1. So we go up 1 to the right 1. And if we were to extend this line, it would have a y-intercept of positive 3. So the expression for this first piece is x and then plus 3. Now the domain here is all x less than or equal to negative 1. It's everything to the left of negative 1 and including. Okay, so for this middle piece, I notice that it's got a negative slope. We go down 1 and to the right 2. So this piece has a slope of negative 1/2. So the equation or expression is negative 1/2 x. And that is between negative 1 and positive 1. And we do not want to include either negative 1 nor positive 1. So this is going to be negative 1 is less than x is less than positive 1. Finally, this last piece has a slope of positive 1. And if we were to extend this line, this would be a y-intercept of 2. So we have x plus 2. Oop, and that reminds me, we missed our y-intercept up here. The y-intercept over here would be 1, 2, 3, 4.5. So 9/2. So there we go. Let's go ahead and include that too. So plus 9/2. Okay, so that last piece, we have x plus 2 is the expression, and the domain is everything greater than positive 1. So x is greater than 1 or equal to 1. And then finally, number 7, or not finally, we got one more after this. We have these 3 pieces here. We have an upward sloping one or positive slope. We have a plateau or a 0 slope, horizontal line, and then a negative slope. So this first piece has a positive slope of, let's see, 1, 2, 3 to the right 1. So the slope is positive 3 over 1 or just 3. And then our y-intercept, if we were to extend this, well, I noticed at this point, -2, 5, or 4. -2, 4 is on this line. If we were to extend it, we would also contain the points -1, 7 and 0, 10. So that tells us that our y-intercept is 10. And this is true for the points, or for the domain x is less than 2, -2. So x is less than -2. Yes, you could say x is less than or equal to, but that's going to affect the domain of the next one. Okay, so the next piece here, we have this horizontal line at y equals 4. The domain here is between -2 and 2. Let's go ahead and include each of those endpoints. So less than or equal to's here. So that means our last piece is going to be strictly greater than. This line is reflected over the y-axis as this first line. So you may have noticed. But this also has a slope of -3 and a y-intercept of +10. So we have the line -3x plus 10 for the domain x is greater than 2. Okay. We'll try one more of these. So this one looks interesting. It looks like we have all horizontal lines. So we'll call this one f of x, real creative with these function names, is equal to the piecewise function. So this first piece here, we have the y value of just 1. Okay. The domain for this is it's between 0 and 2, including 0. So 0 is less than or equal to x, but not including 2. So it's less than 2. For the next piece, we have the horizontal line y equals 3. And this is between 2 and 4, including 2, but not 4. And finally, we have that horizontal piece y equals 5. And this has domain between 4 and 6, so including 4, but not including 6. All right. Let's try modeling. So here we have an online purchase. Shipping costs $6 on purchases up to $50, $8 on purchases up to $50, over $50 up to the $100, and $10 on purchases over $100 up to $200. Write a piecewise function for these charges and give the domain and range. Okay, so I'm going to call this piecewise function. We're talking about shipping costs, so I'll just go ahead and call it S of X for shipping. And we have the first part. So shipping costs $6 on purchases up to $50. So this is a function, the shipping cost per how much you spend, so on the purchase price. So we know that the shipping is going to be $6 for purchases that are from 0 to $50, right? Now we have to determine what those inequalities are. So we know that if you buy nothing, if you spend $0, you shouldn't be paying anything on shipping because you didn't buy anything. So we don't want to include 0. We do, however, these are purchases up to $50. So if I spend $50, I should be spending $6 on shipping. So we do want to include that in the domain of this first piece. For the second piece, we're spending $8 on shipping, and that's a flat rate, $8. Doesn't matter between that range how much you spend. You're going to be spending $8. Now the range here is going to be from 50 to 100. I should say domain here is from 50 to 100. So if you spend $50, then you're going to be spending $6 on shipping. But if you spend more than $50, so over $50, then you're going to be spending $8. And that's all the way up to and including $100 purchases. And finally, you'll spend $10 on shipping from purchases over 100, so greater than 100, but less than or equal to 200, so up to 200. The domain in this case, so what are the x values that we can plug in? Well, purchases all the way from 0 to 200. So let's go ahead and use our interval notation. Now, do we include 0? Is 0 a valid purchase? No, but like 1 penny is, so we're not going to include 0. Can we make purchases up to 200? Yes, we can. So that's going to be a square bracket. So here's our domain and interval notation. Our range, so this is going to be all of the shipping costs. So all of those y values that we would get. Well, we're only paying these flat rates of 6, 8, and 10. So our range is just the set of 6, 8, and 10. This is not an interval. It's simply these discrete values, 6, 8, and 10, because we're not spending anything in between 6, 8, and 10. Okay? All right, so this has been our notes today on piecewise functions. We'll get a whole lot of practice on this in class, so we'll see you tomorrow. Have a great day, everybody. Goodbye.